Hello, welcome to our video on logarithmic functions. This is our last little quote-unquote review video. This is our last time laying the groundwork before we get into limits, which is a uniquely calculus concept. Logarithmic functions, they're related to exponentials. Now, this is an underrated fact. It's important to know that we're only talking about positive x's here. And we're going to have this a show up again with the same properties that we had in the last video. We have this thing log base a of x. This is how we say it. Logarithms have this little subscript number, which is the base. And this base is the same base that you would see in an exponential. These are intimately related. What this means is that you can figure out any logarithm based on an exponential. Exponentials are a little bit easier for us to think of. So that'll typically be how we think about it. So rather than merely memorizing this, I think a very helpful observation is to notice, well, same base, first of all. The base of the logarithm is the base of the exponential. And furthermore, the x's and the y's switch roles here. So with the log, x is the input. That means it'll be the output of the exponential. And likewise, y is the output of the log, which means it's the input of the exponential. So that's the key takeaway. This will help you remember this relationship. Let's do some examples. Say we want to find log base 3 of 9. Let's call this y. We want to solve for y. To do that, think of it in terms of the exponential. Base 3. Now y is the input. And just notice that I switched the order of these. Doesn't really matter how you write that. Okay, so 3 to some power equals 9. Well, that means y is 2, because 3 squared is 9. Therefore, log base 3 of 9 is 2. So to solve a logarithm, think of it as the reverse of an exponential. Next, log base 2 of 1/8. We want to solve that. Let's call it y. Think of it in terms of an exponential of base 2, y now being the input. and 1/8 now being the output. Notice I put parentheses this time around the 1/8. Just a quick note, I could have done the same thing up here with the 9. It's just we don't always do that. I think with fractions it looks better to have the parentheses, but it means the same thing. All right, anyway, we need to solve for y. Well, 2 and 8 certainly have a special relationship because 2 cubed is 8. But here we have a fraction 1/8. 8 is in the denominator. So from an exponent standpoint, what that means is that this is a negative exponent. Y equals -3. Because if y were 3, then our answer would be 8, but instead it's 1/8. So that means it was just a -3 exponent. Therefore, log base 2 of 1/8 is -3. Now let's discuss properties of logarithms. Very important. Property 1. Whenever I'm taking a log of a product, xy, I can write this as a sum of two separate logs. Splitting this into log base a of x plus log base a of y. And notice that this actually goes both ways. These are equal. So I could, if I start here, I could expand to a sum of simpler logs. Or if I wanted to, if I started here, I could condense into just a single log of a product. Sometimes it's convenient to do one thing, sometimes convenient to do the other. That just depends on a case-by-case basis. This one is similar. If I have division inside the log, this is equal to the difference or subtraction of two simpler logs. This one is very important for solving equations. We'll talk about that in a little bit. If I have a log of an exponential, this is a convenient way to get rid of this exponent, get rid, quote unquote. It's not like r is totally gone, but you can make it so that it's no longer an exponent. Again, I don't have to write these parentheses anymore. So the r is now out front times the log. No more exponents are involved. So that is very nice for getting rid of exponents. All right, these next two are just special particular values. Say I have the function log base a of x. So if I plug in a for x, so same as the base, this will always be 1. And the reason for this, if you think in terms of exponentials, this is because a to the 1 is always a. Now there are a few a's floating around. Those a's are the same, the base of the logarithm and the base of the exponential. And this a, the input of the function, is the output of the exponential function. A similar one, if you plug in 1 into any logarithmic function, then you will get the output of 0. And this is because a to the 0 is always 1. These next two you can think of as canceling properties. The exponential function a to the x and the logarithmic function log base a of x, they have a very special relationship with one another. They're actually inverse functions. Now, we're not getting too deep into what that means, but essentially, when we chain them together like this, like I'm taking log first and then plugging that into the a to the x function, these processes cancel out, and I'm just left with x. Whatever's being plugged into the log here. And similarly, if I plug in a to the x into the log base a function, they're inverses of each other, so they essentially cancel, and we just get x back. This is also useful for solving equations. If you say, want to get rid of a log, or if you want to get rid of an exponential. Let's see this in action. Log base 2 of 2 to the x plus 1 equals 4. Well, if this were the plain old 2 to the x, that is the inverse function of log base 2. So these have a special relationship with one another. I'm applying this property 7, where these things essentially cancel out, and we're just left with that power x plus 1. And then that's a whole lot easier to solve. Subtract 1 from both sides, and x equals 3. Let's look at another one. Ln of the square root of 3x. We want to expand this. So first off, what is ln? I want to write that in a different color. When we say ln, this is just a special logarithm. We call this the natural log, or the natural logarithm. And this is literally log base e. E is a number. Like pi, it's an irrational number, which means the decimal goes on forever without repeating patterns, but it's roughly 2.7. So when we write this e, that's a number. The log base, the number e, we call that natural log, ln, because it has a lot of natural real-world applications. So we'll be seeing this one a lot in the course. Really, it's the best logarithm in my opinion. So how do we expand this? Remember, we had a handful of relationships, these first three properties, which allow you to take these shorter logs and expand them out into larger expressions. So that's what we mean by expand. First off, remember that you can think of the square root as an exponential, taking 3x to the 1/2 power. And this means that we can start by applying that third property, which deals with exponents inside the log. You essentially move it out front. So this becomes 1/2 times natural log of 3x. So already that's a lot simpler. And here I have a product inside my log, which means I can use the first property right here. And I have a product inside the log. I can expand it out as a sum. So still 1/2 times ln of 3 plus ln of x. And then we finish by distributing the 1/2. And that's as expanded as it gets. So this is equal to what we started with. This is just a more expanded form. You have more logarithms involved, but the benefit of this is that these are simpler logarithms. I want to say real quick that ln of 3, that looks a little complicated, but when you deal with these sorts of things, remember that it's just a number. It's a weird number to be sure. It'll be some long decimal, but ln of 3 is just a number. So remember that when you're doing algebra. ln of x, on the other hand, that's a function. Depends on what x is. Let's solve a couple of equations. Log of x squared plus 4x minus 5 minus log of x minus 1 equals 0. Notice I didn't write a base. So this is another special kind of log. And your scientific calculator should have a button for this, just like it does for natural log, ln. But if you just see log, no base, that just means base 10. So those are the two special types of logs that you run into. ln, natural log, that's base e. And if you just see log, that means base 10. So we just omit the 10. Because our number system is built around 10, So it's a pretty natural choice. So to solve, I see a couple ways we could do this. I'm going to pick one. But just a quick note, I could add this to both sides, which would essentially be moving that over. And then you could cancel off the logs, but I want to do this a different way. I'm going to use property 2 to condense that. Property 2, remember. So here's a difference, which means I can rewrite it as a single log of this division. So this becomes a single log of this rational function. Now I can further simplify this by reducing if I factor that numerator, that's x plus 5 times x minus 1. We'll notice that the x minus 1 factors cancel, which means I'm left with just log of x plus 5. Now, this is still not obvious what to do, because I cannot just subtract 5 from both sides. This plus 5 is happening inside a log. This means what you have to do is get rid of the log first. If you want to get rid of a log, you apply its inverse function to both sides. Log base 10 and 10 to the x. So plug in log of x plus 5 into the 10 to the x function. You have to do this to both sides, though. So 10 to the log of x plus 5, that cancels off the log. And over here we have 10 to the 0, which is 1. So don't forget to apply that 10 to the other side. And now we can finish. X equals -4. Now, we must be very careful when solving these log problems. This is because the logs are very particular. You can only plug in certain things to them. We need to check the domain. And domain means allowed x's, which you can plug in. There are only a certain limited amount of x's which make sense in our equation. And what I'm getting at is the very first thing I wrote in this video. You can only have positive things go into a logarithm. That's very important. So that means that -4 is a bit suspect as an answer. So let's look at the original problem. If when I plug in -4, I get something negative, inside the log, then that's a problem. And we'll certainly see this happening over here. So I'll focus on this one. You only need it to fail in one spot, and then the whole thing falls apart. So log of x minus 1, if I plug in -4 for x, that's log of -5. This does not exist. Only positive numbers can go into a log. And this is true regardless of what base you have. So if this were ln, this would still be a problem. For any type of logarithm, you must plug in only positive numbers. 0 also will fail. What this means is my answer that I got doesn't work because it leaves us with undefined logarithms in the equation. Turns out these actually both fail. For this reason, there is no solution because the only thing that could have worked doesn't. So this is the real answer to the problem. We had to throw out our solution of -4 because it's incompatible with the logarithms that we see. So when you're solving logarithmic equations, that's something that you have to consider. When you get to the end of the problem, you have to make sure that when you plug the number in, all of your logarithms are defined. Last problem. We're actually going to solve an exponential equation. Feels like a throwback to the last video. This is different though. This is different from what we did in the previous video because these bases are completely incompatible. There's no way to rewrite this to have the same base on both sides. There is no common base and no manipulation that you can do to get a common base. The trick then is to apply a logarithm to both sides. Now, do I do log base 2 to get rid of this 2? Well, that wouldn't work very well over here. Likewise, if I tried to apply log base 3 to both sides, well, that would cause us problems here. What I would do instead is just use ln. I will say that actually any logarithm will technically work, but ln is the best natural choice. Let me show you why. So I apply ln to both sides. Notice that ln is log base e, which means it will not cancel off this 2, and it also will not cancel the 3. But we get the next best thing. The next best thing to canceling is property 3. this exponent can come out, and then it's not an exponent anymore. So this x plus 1 can come out as a factor. Likewise, this x can come out Now this may look slightly complicated with ln of 2 and ln of 3, but remember that these are just numbers. These are constants. Now we prefer to leave them as ln of 2 and ln of 3 because they're nasty decimals. But when we're doing algebra, think of them as constants because they are. So now we can do algebra to solve for x. It's actually still not the easiest algebra problem in the world, but it's doable. First, let's distribute this ln of 2. Plus 1 times ln of 2, just ln of 2. So I just distributed that. Now let's put the x terms together. I'm going to subtract this from both sides. Okay, that's my operation I'm doing. I'm trying to get the x terms together. Leaves me with 0 over here. Now let's get the non-x things on the other side. So I'll subtract ln of 2 from both sides. Great. Now to get x by itself, and this is maybe the trickier part, notice that on this side, now that I've moved the ln of 2 over, I have a times x in every term, which means we can factor it out. Now this ln of 2 minus ln of 3, that's still just a number. So we have x times some number equals some number, which means we just divide both sides by this number. Even though it's a bit of a messy one, we can still do this. Oh, I like to highlight my algebra steps. There we go. That's a nasty complicated number, but still just a number. So we are done, except I might want to simplify this a little bit. This is okay, but this is a negative over a negative. It turns out ln of 3 is a bigger number than ln of 2. So we can clean this up just a little bit. I've got a negative over a negative, so cancel those negatives. So this difference here, if I multiply that by -1, then this will be the positive part. And I'll just write that first. And the ln of 2 is now the negative part. So in that step, I just took the negative of both the numerator and denominator. This is a little bit cleaner. This is also fine, but we could do even a little bit more, and it's good for us to use our properties. Notice this denominator is a difference of logs with the same base, e. I can combine that, I can combine that into a single log of this quotient or division. I'd say this is the most simplified version. These previous two answers, they were okay, but this is the most simplified version. Now, when I have a log divided by a log, there's really nothing you can do with that. There's no special property for that. All right, well, next time we'll get into limits. That'll be our first step into uniquely calculus territory. See you next time.